There is a smudge at the center of our galaxy, not visible to the naked eye, not something you can point to on a clear night and name without a telescope, just a region of sky in the constellation Sagittarius, hidden behind so many layers of gas and dust that no visible light escapes. But something is there. And right now, without any sensation of motion, without any awareness of speed, Earth is falling around it at 828,000 kilometers per hour. It takes 225 million years to complete one orbit. We have never completed a single lap, not once in the entire history of life on this planet. That object is Sagittarius A star, the supermassive black hole at the gravitational center of the Milky Way. So let's ask a simple question. How long would it actually take to reach it? Not approximately, not poetically, actually. Because the answer is not what you expect, and the reasons why are stranger than the number itself. 26,000 light years. Your brain cannot process what that means. So here is the comparison that should stop you cold. If you shrink the entire solar system to fit inside a football stadium, Earth's orbit around the Sun becomes the 50-yard line. At that scale, Sagittarius A star sits 4,400 kilometers away, the distance from New York to Los Angeles. Our fastest spacecraft at that same scale moves at the speed of a garden snail crossing a sidewalk, but it compounds. We are not starting from rest. We are already moving, fast. Earth orbits the galactic center at 828,000 kilometers per hour. That is not a choice. That is where we are. And at that speed, one complete orbit takes 225 million years. 225 million years. The last time Earth was at this exact position in the galaxy, dinosaurs had not evolved yet. The supercontinent Pangaea had not formed. Life was still figuring out how to leave the oceans. We have never completed one lap, not once in the entire history of our species. And this creates a problem. To reach Sagittarius A star, you cannot simply point a ship toward it and accelerate. You are already moving sideways at 828,000 kilometers per hour. You have to cancel that orbital velocity first, burn fuel to slow down, stop, reorient, then burn even more fuel to accelerate inward at speeds far higher than the velocity you just cancelled. This is not a minor inconvenience. It is a mission-defining constraint. The fuel you spend cancelling Earth's galactic velocity is fuel you can never use for the journey itself. It is gone before you have traveled a single light year toward your destination. You are starting in a hole, and the hole is 828,000 kilometers per hour deep. Every kilogram of fuel burned to decelerate is a kilogram you cannot use later. Every second spent slowing down extends the total mission time. And there is no refueling station at the halfway point, no resupply convoy, no backup plan. The distance does not just measure space. It measures every engineering problem you have to solve before departure, every constraint that compounds once you leave. Let's be generous. Voyager 1 launched in 1977, nearly 50 years in space, the farthest human-made object from Earth. Right now, it is 24 billion kilometers from home, well beyond Pluto, drifting through the space between stars. It moves at 61,200 kilometers per hour. At that speed, traveling non-stop towards Sagittarius A star, the journey takes 456 million years, not 1,000, million. 456 million years ago, the first vertebrates were just beginning to crawl onto land. Humans would not exist for another 455.7 million years. If Voyager 1 had launched towards Sagittarius A star At the very beginning of vertebrate life on land, it would still have 200 million years left to travel. The entire age of dinosaurs would have come and gone during the journey. Mammals would have risen, diversified, and produced a species intelligent enough to build a second spacecraft, and that spacecraft would still not have arrived. Let's go faster. The Parker Solar Probe holds the speed record for any human-made object. It uses the sun's gravity as a slingshot, diving closer and closer to the solar surface until it reaches 692,000 kilometers per hour, more than 11 times faster than Voyager. At that speed, pointed directly at Sagittarius A star, the trip takes 40 million years. 40 million years is longer than the entire primate lineage. It is 10 times longer than hominids have existed. And here is what makes this worse. The Parker Solar Probe reaches those speeds only by falling toward the sun. It uses gravity as a free accelerator. That advantage disappears completely in interstellar space. There is no star to slingshot around, no gravity well to exploit. Whatever velocity you launch with is the velocity you maintain, unless you burn fuel to accelerate. And fuel has mass. More fuel means more mass to accelerate, which requires even more fuel. The equation compounds before the mission even starts, so that 40 million year estimate is a best case. For a ship traveling under its own power, with no gravitational assists available across 26,000 light-years of open space, the real timeline gets worse. But there is one more option. And for exactly 12 seconds, it looks like a way out. Nothing with mass can reach the speed of light. Not because we lack the engineering, because the universe prohibits it. Accelerating any mass to light speed requires infinite energy. Infinite energy does not exist. This is not a technological gap. This is physics. But let's approach it. Suppose we built a ship that could reach 99.9999% of light speed. Not realistic, not achievable with any known technology, but theoretically possible. Something remarkable happens. Einstein's relativity shows that time does not pass uniformly. The faster you move, the slower time passes for you relative to stationary observers. This has been measured. Atomic clocks on jets tick slower than identical clocks on the ground. GPS satellites require constant corrections, or their positioning would drift by kilometers per day. These are not theoretical predictions waiting for confirmation. They are engineering realities that your phone depends on right now to tell you where you are. At 99.9999% of light speed, time dilation compresses the journey. For every 700 years that pass on Earth, only 1 year passes on the ship. Apply that to 26,000 light years, and the crew experiences roughly 37 years of subjective travel time. 1 human lifetime, 1 generation. There is also length contraction. At near light speed, the galaxy itself compresses in the direction of travel from the crew's perspective. What looks like 26,000 light years from Earth appears as only a few dozen light years to people on board. Space physically reshapes around their motion. On paper, this looks survivable. It is not. Interstellar space is not empty. It contains hydrogen atoms, approximately 1 per cubic centimeter. That sounds sparse, negligible even. At human walking speeds, you would never notice. At 99.9999% of light speed, a single hydrogen atom strikes the ship with the kinetic energy of a high-velocity rifle round. Constantly, billions of impacts per second, for 37 years. A grain of dust, something you could barely see, hits with the force of a tactical nuclear weapon. The shielding required would need to be meters thick, constructed from the densest materials we can manufacture, so heavy that accelerating it to near light speed becomes energetically impossible. And that shielding would erode, particle by particle, impact by impact. For decades, the front of the ship gets thinner, year by year. There is no repair schedule, no replacement panels waiting in a storage bay. Whatever you launch with is all you have. One breach, anywhere in the hull, at any point during the 37-year journey, and the mission ends instantly. Then there is the radiation. At near light speed, starlight ahead of the ship blue shifts into higher energies. Visible photons compress into ultraviolet, then X-rays, then gamma rays. The cosmic microwave background radiation, normally harmless, shifts into lethal frequencies. The front of the spacecraft would be bathed in continuous gamma radiation, intense enough to sterilize the interior in minutes. And this is not radiation in the sense of a medical scan or even a nuclear power plant. This is sustained, concentrated, high-energy bombardment with no natural pause and no shielded room to retreat to. The entire forward face of the ship becomes the exposure surface, every hour, every day, for nearly 4 decades. The particle bombardment and the radiation are not separate challenges you solve one at a time. They compete. Thicker shielding absorbs more particle impacts but adds mass that makes acceleration harder. Lighter shielding makes radiation management easier but fails faster under impact. Every design decision pulls against every other decision. There is no configuration that solves both cleanly. To reach 99.9999% of light speed requires continuous acceleration. As velocity approaches light speed, the energy required for each additional fraction of a percent rises exponentially. The curve does not increase in a straight line. It rises steeply. Then it goes nearly vertical. Even with perfect matter-to-energy conversion, antimatter propulsion, anything theoretically possible, the energy needed to accelerate any useful mass to 99.9999% of light speed exceeds what we can store or generate. And that fuel has mass, which you also have to accelerate, which requires more fuel. There is a mathematical relationship that governs this. It is called the Tsiolkovsky rocket equation. And for relativistic velocities, it shows that the fuel mass required exceeds the available material in most planetary systems. This is not speculation. The math does not care about your engineering. It does not care about your intentions or your ingenuity or how many generations of scientists work on the problem. The equation is what it is, and what it says is that the fuel required to push even a modest spacecraft to near light speed and then slow it down again at the destination is not merely large. It is cosmically, absurdly, physically impossible to carry. You would need to harvest entire planets just to begin. But the fuel problem is not even the first wall you hit. There is a moment, much earlier in the journey, that seals the outcome. It happens when the fuel required to decelerate, reverse, and return exceeds the fuel the ship can carry. After that point, continuing is the only option. You cannot simply accelerate and coast. You have to decelerate at the destination, then accelerate again to return, then decelerate at Earth. 4 burns. Each requires fuel, and the fuel for later burns has to be carried through earlier burns. For any realistic mission, the point of no return arrives within the first few percent of the journey. Once you burn enough fuel to reach a certain velocity, you no longer have enough remaining to reverse course. The mission becomes one way, not because you failed, because the physics does not permit otherwise, and communication stops being meaningful even earlier. The crew experiences 37 years. Earth experiences 26,000. While one generation lives and dies aboard the ship, 26,000 years of history unfold back home. Everyone who built the ship dies, their children, their grandchildren, every descendant for hundreds of generations. Governments rise and fall. Languages evolve beyond recognition. The words used to name this mission, the agency that funded it, the country that authorized it, are all gone, replaced by something so different it would be unrecognizable to anyone alive at launch. Civilizations collapse entirely, multiple times. A message from Sagittarius, a star, takes 26,000 light-years worth of travel time to reach Earth. The reply takes another 26,000 years back, 52,000 years round trip. By the time Earth hears the ship arrived, the civilization that sent it does not exist anymore. From the crew's perspective, they sent a message 37 years ago and never heard back. They will never hear back. The ship and its crew become, from the moment of departure, entirely self-contained, entirely alone, in a way no human mission has ever had to be. Not the isolation of Antarctic winter stations, not the silence of deep ocean submersibles. Something categorically different, a separation so complete that the concept of home stops having a meaningful referent. There is no home anymore. There is only the ship and the dark ahead. Suppose, hypothetically, you solved it all. Built the ship, fueled it, survived the journey. Sagittarius. A star is not a destination. It is an event horizon. The Schwarzschild radius, the boundary of no return, sits 12 million kilometers from the singularity. Closer than Mercury orbits our Sun. Cross that threshold, and something changes. Fundamentally, every direction you can travel, including backwards through time itself, points inward toward the singularity, not as a metaphor, geometrically. The curvature of space-time becomes so extreme that outward stops being a direction that exists in your reference frame. You do not crash into a wall. You do not hit an obstacle. You simply run out of possible futures that do not end at the center. The innermost stable circular orbit sits roughly 3 times the Schwarzschild radius out, approximately 36 million kilometers. Closer than that, and tidal forces begin to dominate. Orbits that look stable start to decay. You spiral inward, inevitably. For smaller black holes, stellar mass black holes formed from collapsed stars, tidal forces would tear you apart long before you reach the event horizon. But Sagittarius A star is different. It is so massive that the tidal forces at the event horizon are surprisingly weak. You could fall through the event horizon of Sagittarius A star and remain intact, alive, conscious, for a brief time. You would just never leave. From your perspective, falling inward, you cross the event horizon in finite time, seconds, minutes, depending on your trajectory. But to an observer watching from a safe distance outside, you never cross. Never. You slow down as you approach the horizon, asymptotically. Your image stretches thinner, redshifted into invisibility, as photons escaping from your position take longer and longer to climb out of the gravitational well. You cross the horizon, and you never cross. Both statements are true, simultaneously. That is not a paradox to be resolved. It is the geometry of extreme spacetime. 2 observers, 2 entirely valid descriptions of reality, with no shared answer to the question of what actually happened. General relativity does not give you a tiebreaker. It simply says both are correct within their own reference frames and leaves you with the discomfort of that. Any ship that gets close enough to study Sagittarius A star in detail, close enough to take measurements, is close enough to risk falling past the point where escape becomes physically impossible. And if you cross that threshold, there is no engine powerful enough to bring you back, no trajectory that leads outward. The mission does not fail, it terminates. So here is the answer. 456 million years with our best current technology, 40 million years with our fastest spacecraft, 37 years of ship time if we could reach 99.9999% of light speed and solve the fuel problem and survive the radiation and avoid the event horizon and accept that 26,000 years pass on Earth and the mission is one way and there is no communication. Those numbers are real, scientifically accurate, but they are not the answer. Sagittarius A star cannot be reached the way the question implies, because reaching it requires carrying fuel that does not fit in any ship we can build, surviving radiation that shreds matter at the atomic level, accepting a point of no return that arrives almost immediately, and approaching an object that warps space-time so severely that the concepts of arriving and leaving stop meaning what they normally mean. The problem was never the distance. It was what distance at this scale does to time, to energy, to the ship, to the geometry of space itself. And once you pass that threshold, the mission does not get harder. It stops connecting to the universe you left behind.